Hello everyone, welcome back to another video lecture. Today I'm going to solve problem 5 of homework 9, which is basically problem 6 from chapter 22. Okay, let's go through the questions first. So question says, as an estimate for the free energy of boring a charged amino acid such as aspartic or glutamic acid in protein cloning, compute the free energy. You have to compute delta G basically for transforming an ion of radius 3 Armstrong, it is radius not diameter, of charge plus 1. So it's given plus 1, we'll assume that there is one proton from water to oil. So the medium is changing from water to oil and the dielectric constant from water and oil is given. So all the data I already write it here. So we'll use this data. So before solving the question, let's see what's the logic or theory behind it. So if you go to page number 447 or 448 of chapter 22, so there is something called Bond's theory or Bond's equation. So there it is explained when a charge is transformed from one medium to another medium. So it's basically its delta G gets changed. So its free energy change either from positive to negative or negative to positive, from a stable state to unstable state, it gets changed. And in that page, if you see equation number 22.61, so they already have computed what will be the net or delta g after like transformation. So I wrote it here, Bond's equation 22.61, which says delta G is equal to fancy rho q square over 2a. So 2a just because a is here radius and 2a just because we have to compute as a whole sphere. So 1 over second medium minus 1 over first medium. Second medium is the medium we are transforming to, and medium 1 is the medium we are transforming from. So this question is basically either solved by however the book solved in 22.313 example, or directly substituting the value. So I will choose like to substitute the values and solve instead of like going through and calculating a Bajarian length and all. So instead of doing that, I'll like use this formula. Okay, so I just open the fancy row. Fancy row is 1 over 4 pi epsilon is q square. So it's given q, but it's already given q is equal to positive 1. So I am assuming it's a positive 1 or one proton. So it will be q square is e square. So also why I am taking the molar or Na. So if you go to chapter 20, page number 386, there is a big table or big calculation of units. They have already converted why we need Na or why it's Na. So we can easily follow that one for that. And because we are calculating for 1 molar, so that's why we are easily multiplying the moles. Number of moles are 6.022 Avogadro number. So that's why the Na is here. Okay, now let's substitute the values. So 1 over 4 pi, the value of epsilon or permittivity is 8.85 into 10 to the power minus 12 joule inverse coulomb square meter inverse multiplied by e square Na. So e square is the charge of an electron or proton. So I can easily write it as 1.6 into 10 to the power minus 19 whole square into Avogadro number 6.022 10 to the power 23 2a. So 2. So a was given 3 Armstrong. We need to convert it to 3 into 10 to the power minus 10 meter or meter. So it will act as 3 into 10 to the power minus 10 meter. Okay. So this is mole inverse, this is coulomb, into 1 over d2. d2 is our oil, so oil is given as 2, so 1 over 2 minus of 1 over 80. And these are unitless because these are constant, dielectric constant, basically ratio, so doesn't matter. So this meter inverse, meter gets cancelled, coulomb square gets cancelled, and if you input this in a calculator, we will end up with something like 112,578.3047 joule mole inverse. This can be also written as electron volt mole inverse. But like this is a very big number. Basically we don't like need this much of big number. We can convert this to kilocalorie. So we know that 1 kilocalorie is equal to 4184 joule. So 112,578.34047 joule. Mole inverse will be equal to 112,578.3047 divided by 4184, which is roughly equal to 2690 kilocalorie mole inverse. So okay, so 26.90 kilocalorie mole inverse. So this is our answer. So you can see like delta G. So this is our delta G. So delta G transformation is positive, which it's not stable. That's why we always say if there is a charged particle, if it moves from water, which is a water is a polar medium, to oil, then it gets unstable. So that's why it's always recommended to like mix the charged particles or charged proteins or charged amino acids like these things in water, and these are miscible in water and immiscible in oil. Okay, that's all for today. Let me know if you have any question. Thank you. Have a good day.